is talk about specifically two types of collisions. Two types of collisions. Now, what we've noticed is, so far, we've had collisions where two objects might collide and then bounce off one another. Then we had collisions where objects might collide, in a sense, and stick together. Max, take it out, please. Now, if we look at an example from last class where the person jumped off of a platform and landed on a cart. So imagine, can we all look up here, please? So imagine you're sitting on like this desk, and you fall off the desk and land on this chair, and you start to slide together. Okay? So it's like I fall off the chair, I land in the desk, I land in the chair, and now me and the chair act as one object. Now, that's the difference between, I kick a soccer ball, it collides with another object, and that object starts to move. So we're going to distinguish between the two. One of the scenarios, the objects stick together afterward, or the objects stay together afterward. The other example, the objects do not stay together. They collide, and then they go separate directions. Okay, that's the differences of the two that we're going to look at today. We're going to describe which is each.
Is this kind of like on the sheet? There was a question of like a football player who like jumped on.
Correct, onto the back of another person.
And
Exactly.
the same way. Okay.
So this is like where two objects collide and they act together afterward as one mass.
It was also like when you hit something at the point where like you start like go in, like elastic kind of like squeeze it and shoot out.
Well, elastic is going to be, that's a good way to remember elastic, because elastic is going to be when they separate afterward. And if you think about things that are elastic, they are like flexible or bendable. So if two objects hit together, they would smack together, like kind of bend. Soccer ball?
You kick a soccer ball, like the soccer ball kind of goes in and shoots out.
Yes. That would be elastic though. Elastic, okay? Now, an example of elastic again, here's how you remember elastic. When two objects collide and then separate, think about a spring. If you were to push down on a spring and then let it go, the object would shoot off. It would become separate from the spring. So elastic is an example where objects collide.
You look like a baby.
Sorry. Objects collide and then separate. Now, for elastic, we could say things are either perfectly elastic, okay, perfectly elastic, or we're going to look at perfectly inelastic. Say again? No, not really. Why don't you just borrow? Just borrow someone's for now.
Are you going to test that before?
Yes, for sure.
Wait, what do you think so far?
You said he's not right.
The multiple choice looked pretty good so far. I didn't say I wasn't happy.
You said
When did I say that? Oh, I don't remember saying that.
just something of that sort.
Now, here's what we're going to notice. For inelastic equations, or inelastic collisions and scenarios, a good example is this. And this happens actually more than you would think. Imagine a car is driving down the road. The first car, or the car, so what's the rule of thumb? If you crash into somebody and your front end of your car hits the back end of their car, you're at fault automatically. Agreed? Now, so in these scenarios, listen, sometimes what happens, believe it or not, is the bumpers will fuse together. And this is actually a true thing. So if one car is coming to a stop at a light and the other car doesn't see the car stopping, and the one car that is behind the front car hits into the other car, sometimes you'll notice the bumpers themselves will actually fuse together because the heat that actually occurs between them. Now, the way to think about that is as if we have an inelastic collision, this bottom one down here. This is when the objects, I'm going to put objects, and I'll put this in quotes, fuse together It's not always from fusion, but I'm going to say fuse together after the collision.
So these are only in specific.
There's specific cases, yes. There's specific cases. So, again, we've looked at both of these cases already. We looked at both of these cases in section 6.2, but we didn't classify them or identify them with these terms. So, elastic is when they collide and then they separate. Inelastic is when they fuse together after the collision. Okay, after the collision. That's one at a time, one at a time. So, the friction between them and the heat between them causes them to melt together so that they're stuck together as one object. There's not a machine? There could be enough heat if you're going at a high enough speed, actually, yeah. It is possible. I'm not making this up at all. It is actually true. I know. You would think, right, that most don't happen this way. But this could happen. And this is a possible scenario.
Good thing it like reduces the amount of impact.
It depends on the scenario. It really does. Depends on how fast the other car was moving and how fast you're moving. A lot of things. Guys, gentlemen, stop.
I feel like T-bone a car like wraps a little bit around
Around the front of it. If they stick together afterward, that's considered to be inelastic. Yeah, and that could happen. Yep.
Wait, it would be inelastic?
Yeah, if they stick together. Yes. Tom.
What if you just throw like two things that are like stiff versus like not fast and then just stick together, like Play-Doh?
That's technically inelastic, yeah. So imagine, ever see those things, oh gosh, what are they called? Students always used to have in my old school, they thought it was funny. They're like these little hands, and they're like, listen, they're like gel, and you go like this, and you can like grab a piece of paper. Alright.
I did that on my cat.
Imagine you took one of those, okay? Imagine you took one of those that didn't have any stickiness left on it, okay? Say it was an old one and it didn't work well. And you went to like do that to Jack's pen. It might knock the pen, this pen. You take the sticky thing and you do that to the pen. It might hit the pen and knock the pen forward, okay? That would be considered elastic because it collides with the pen and pushes it. But if the sticky hand had some stickiness left on it and you actually did that, it would actually pull it backward towards you, right? It would collide with it and they would stick together or they would fuse together. That would be like an inelastic collision.
Yeah,
Now, Max, go ahead.
even if you use like a belt or something, you can still pull it towards you.
Sure, but the idea is that you're actually one object afterward. It's not a matter of pulling it towards you or pushing it away from you. It's a fact of after the collision, the objects are together. So for example, remember the person that jumped into the shopping cart, before the collision, they're separate. But once I jump into the shopping cart, now I'm in that cart. And now me and the shopping cart act as one object. Okay? We act as one actual object. Now, what we're going to see today is the following. If the two objects fuse together, what does it take for two objects to melt together? What do you need? Heat. And to have heat, you need what? Some sort of a source of energy. So, we have friction. This is the example where we're not going to have an energy balance. We're going to have that Q loss. Remember Q loss? The loss of energy? Okay? So here's what we want to write down for the following. Please jot this down. For elastic collisions, the kinetic energy of the objects beforehand equals the kinetic energy of the objects afterward. KEI equals KEF. Again, for elastic collisions, the kinetic energy beforehand equals the kinetic energy afterward. Now, when the objects fuse together, you lose energy to thermal energy or heat or friction. So what that means is that the kinetic energy beforehand is not equivalent to the kinetic energy afterward. What you'd have to write is the following. Okay, so again, the kinetic energy beforehand equals the kinetic energy afterward, plus now some Q loss. Again, where does that Q loss come into account? Think about what it takes for two objects to melt together. If you want to melt two objects together, you need to apply some form of heat, some heat source, so that the objects actually do melt together.
So QLS is like friction.
Yes. Okay?
Everyone was scared you were gonna put that in the test. QLS? Yeah.
I wasn't scared.
I was afraid.
Don't speak.
I took it as a challenge.
Any questions on this so far? Are the ideas there?
What's the formula QLS?
It depends on the problem, but traditionally F cosine theta x. The force over the distance.
It's just so many different possibilities within one. Like
Yeah, it's true, and they're all linked to each other. Like energy, we still have forces of friction and work. Well, we also have
traditionally QLS
This only gets harder.
F cosine theta x. The thing is, there's more material, but by the end of the year, you're going to realize how they're all related to each other, and it actually gets easier because you're like, oh, this is just this is just this.
You get a new formula every day.
You do.
There's like 365 formulas.
I mean, I don't think there'll be that many, but there'll be a lot. It'll probably be at least a half a page. You know how it's like a quarter a page now? It'll be down to at least a half a page by the end of the year of formulas.
We get all the formulas on the paper.
Oh, you did it yesterday. Very good. I'm glad. That was a good way, guys. I'm glad Miss Baber told you yesterday. Miss Baber told you? Baber told you yesterday? I'm gonna give you a topic list tomorrow for the midterm, a topic list. In addition to that, I'm gonna give you sample questions to practice over break. Okay? So it'll be a good review. In addition to that, I'm gonna put up all your tests 1 through 5 on Moodle, and that's a good source to study from, especially for your multiple choice. Okay? All right, let's go into an example of this now. Say again?
Yeah, so we can give them to the sophomores next year.
You'll have the answer key up there, yeah. They'll both be there. But you should really do them as if you don't have them. Yeah. It would help you a lot. All right, so here's the example. Ready? Guys, don't touch those, please. Here's the example. We've got a car stopped at a light. So here's the example. We've got a car. Here's a traffic light. First car is stopped here. It's an old school car, right? It's a DeLorean. It's in the Back to the Future car. Now, another car. So, by the way, this car is going forward that way. Sorry, even though it doesn't look like it. Another car or truck of some sort. It looks like a Batmobile.
Oh, yeah.
It's a station wagon. Okay? So an old boxy station wagon rear ends a car that stopped at a light. I don't know how you expected that to go in, by the way. Aerodynamically, it doesn't make sense, right? I mean, it's like, Jeff, it's like me doing this. Ready? I'm going to throw this into the garbage can.
Mine was like a little ball.
It didn't look like it. I don't
Your
know.
velocity was under 2. How did you expect that to get to the
So, we've got a car of, let's say, 1,850 kilograms.
Oh, this is the back of the
Can't believe we did it wrong. I did it in class.
The other car is 975 kilograms, so the truck. Or a station wagon, whatever it may be. So, before this car collided, it had a velocity of 22 meters per second. Now, the red car is at rest, or it's stationary at the light. So the red car is sitting there, gets collided with by the station wagon, and the two cars fuse together. Their bumpers stick together. So, for a problem like this, what kind of a scenario do we have? Yes, is it inelastic? Or yes, is it elastic? Masha, why? Inelastic, how come? And they remain together. Again, let's write this down. This is inelastic. Okay, again, how do we know it's inelastic? Because these two objects collide and stay together afterward. So this is an example of an inelastic collision. Paul.
So if they collide, but then it still moves, the first car, like the car in front is still moving.
So if they collide like this, and then they move together and stick together like it is, it's inelastic.
Oh, it's still inelastic.
If they collided and then separated, they could still move.
So is there VF2?
Well, that's the thing we have to figure out now. They're together, so there's only just a general VF now. Okay? All right, momentum equations. Beforehand, we've got the mass of the first object times the initial velocity of the first object. We also have the second object beforehand. Even though it's not moving, we're gonna drop it off in a minute. So beforehand, that's what we have already. Again, the first object is moving, so it has some momentum. The second object is at rest, waiting at the traffic light, stopped, so there is no V2I, so we can put that goes to 0.
So we're looking for the final velocity?
We're trying to figure out the final velocity of the cars afterward when they're stuck together.
So it's
This next part is the trickiest part that people mess up. Fernando, go.
M1 plus M2 in parentheses with V2 F or VF.
Yeah, just VF, good, because there's no 1 or 2 anymore.
Gotcha.
Again, we've got two cars colliding. The first one is at rest, so we put V2I as 0, so that drops off. The second car is in motion. Afterward, they stick together, so it's as if they're one car afterward. So we put the masses as M1 plus M2. They have only one velocity together afterward, and we call that VF. Let's solve for VF now. And by the way, remember what I mentioned at this point? If you want to plug in numbers, this is the one example in this year that I'm going to say that you might want to use numbers. You don't always have to solve algebraically for this one.
That was just that problem. Just that any of these questions.
Any of these momentum ones seem to get confusing with the subscripts, so I sometimes encourage to just solve with numbers, but you can solve algebraically.
No, never mind. I was about to say you could divide the M1, so take out the M1s. Can you do that?
Well, you can divide by this, but you can't take them out.
Wait, why would we?
Again, we're looking for VF. I don't feel like everybody's focused today. Come on. I understand that, but we're still doing work, guys. We have a lot of work today, tomorrow, and Thursday. And Thursday we have a double period. It's going to be a full double period. Okay, so get ready for it. Get yourselves in the motion. Now, we want to get VF by itself. So we divide by M1 plus M2. That cancels. This portion is 0. So I don't have to worry about it. Now, why is this 0 right here? To make it clear that it's 0. Sorry. Now, all we have left is this portion right here. Okay, that's all we've got left here. M1 V1I over M1 plus M2. Let's take a look at what we get. If we plug in 975 times 22 over 1850 plus 975. Good. We should get 7.6 here.
I got 7.68, so there's not much of a difference. There's not really much of a difference.
Olivier's being so mean. I don't know that.
Nice girl. Nice guy. Those ones are easier. Sounds like a little jealous. Other ones before this.
Seriously.
Now, here's what I want you to try next. Here's what I want you to try next. Go ahead, calculate, and be careful when you do this. Calculate the kinetic energy before the collision of each object. Listen carefully. Calculate the kinetic energy of each object before the collision. Then calculate the kinetic energy of the objects lumped together after the collision. Okay? Again, first calculate the kinetic energy of the objects. And here's what the scenario we have. Whoops, let's go back. Here's the scenario we've got here. I want you to calculate the kinetic energy of the objects before the collision. Then find the kinetic energy of the objects after the collision. Go ahead and try that on your own. Take about a minute or two to do that. Use your calculator, please.
What would you add in Kulas?
We're going to talk about that in a second. Just calculate kinetic energies first. You'll see it if you do that. It'll help a lot.
Is that the same thing that you do when you were talking about the bullets on the problem set? That you have to set up two kinetic energies and then you have to figure that out, or is that different?
Oh, it's the same idea, but I'm just asking you to calculate the kinetic energy. So it's the same idea, but again, calculate kinetic energy.
Wait, we're just doing KI.
Again, guys, all you're doing is calculating the kinetic energy beforehand and the kinetic energy after. You're not writing an equation
Of which car?
of all the objects. So, for example, car 1 and car 2 beforehand, and then the combination of the cars afterward, because they're fused afterward. Calculate kinetic energy before.
Not doing an equation because that looks like it would be pretty.
I didn't tell you to do that. I said find the kinetic energy before, find the kinetic energy after. I didn't say they're equal to each other. I'm just saying find them individually. So your goal is this. Find this and find this. Find them separately. Okay? Find them separately. Think about what's going on beforehand. You have one car moving beforehand, not both. So only one of the cars is going to contribute to the kinetic energy beforehand. The other car is stationary.
Oh, the first car station.
One of the two is stationary. You have to be careful as to which it was.
So if you get them before and you get one object and both objects, when they collide, all you have to do is add together the velocities in your I got it. I just don't know what to do after you get the both objects.
I don't know what you're asking me, Max. It doesn't make sense what you're saying.
Are they big numbers?
They're probably big numbers, yeah, because you're going to be squaring large numbers.
Okay, so let's say you get the, because you asked us to find both objects before the collision, and then after the collision as one entity. So to find it after the collision as one entity, you have to add together the velocity.
Not the velocities, the masses. We have the velocity VF. We found it. Remember?
That was just.
That was the velocity of them together afterward.
Each of them before.
And then the kinetic energy as a whole afterward, as a group. Okay?
Isn't KF what you solve for before? Oh wait, no, we solved for.
That's what you should have if you haven't done that so far. Okay, not the numbers, but just the variables at least. This is going to go to 0 because V2I is 0. So we can drop this off. And all we're going to have beforehand is the one car by itself. But then afterward, remember, aren't these cars now stuck together? So their masses are together. And the final velocity afterward is the velocity that we solved for a minute ago. When you have an answer, raise your hand so I can get an idea. Tom? Just give me the first one at least, or some part. What do you got for me, Tom?
Like first and not second, but that's how you do it.
That's fine. I just don't know if the numbers are right. Just tell me which is which time.
235,000.
Concur?
Yeah, we got the same thing. So.
For which one? The first part or the second part? Go ahead. 200 and.
35,950.
All right. That's what we have for the first one. Check that answer, please.
235,000.
And the second one, Tom?
81,586.
Do people agree with those numbers so far? The first one I already got a few agreements with. The second one. Check that number, please. Remember, lump the masses together first. Multiply it by 1/2. Then multiply it by 7.6 squared.
I get that.
You got it?
I mean, I just don't get how. That's.
We're going to talk more. We're not done. Okay, here's what I want you to notice. Wherever you are, stop and look up, please. These numbers are clearly different. They're clearly different. Stash, answer your question that you asked me right before the question started. Why are these numbers different here? What is the contributing factor to this? Yeah, Q loss. So where would Q loss go in this part? Where would it be making up for? Would it make up for a number down here or a number up here?
When you say making up, what
Like there's a difference between these numbers.
like you can see that it's in the bottom part, right?
If you consider Q loss to be positive, it would be down here, right? If you consider Q loss to be negative, it would be up here, taken away. But the idea is this. The collision was inelastic. So these two objects fused together. To fuse together, you need heat. Now, if you have some loss of energy to heat, your kinetic energy is not going to be balanced. So where is the energy lost to heat? How much is it? What's the difference between these two numbers here? Just subtract them. If you want to know what Q loss turns out to be, or the energy that caused this collision to be inelastic, or for these two objects to fuse together, the difference of these two numbers is that value. Okay, so Q loss is simply the difference in these two numbers. So far, so good? Yes? No? Maybe so?
Yes.
I sure hope so.
Ron.
Actually, it's the same word. So,
Yes, sir.
It is 174,000. Okay, check.
You're always going to lump them together when it's elastic. Yeah.
It's
This is always going to happen.
Inelastic.
Gucci.
Oh, elastic?
Yeah, elastic.
They would not be lumped together. The kinetic energy afterward would be the same equation as this Jeff right here, except that would be an F, and that would be an F now, because it would be the velocities after the collision. Guys, have a good day. We'll continue tomorrow with it. So again, let's reiterate real quick. Before we verify the kinetic energies, first, we had two objects moving head-on elastically, so we separate their masses. We know they have different masses initially, and different velocities initially, and they have different masses. Now, we also know the fact that we have the final velocity of one of the objects. We notated the negative for the west. We went ahead and put our equation here because the objects are colliding elastically. Elastically. Okay, so the masses are separate afterward. We got a final velocity of the mass with 25 kilograms. If we want to verify this with the kinetic energies, we need to go ahead and calculate those kinetic energies. So let's go ahead and calculate KEI and KEF, please. Somebody, before we do this, tell me from yesterday, if you remember, or if you need to look in your notes, what should these values be? And not the exact numbers, but give me some sort of a point here to make.
Are you asking for like 1m, 1/2 of b squared?
Well, there, those are the formulas. But what should they be with regards to one another?
Oh, they should be negative and one should be positive.
Not negative and positive. Fernando, help me out. Equal. Equal to each other. Stash, why are these two equal? Why should KEI be equal to KEF? Theoretically, obviously. Yes. Remember, elastic collisions, there is no deformation The objects are not fusing together to one another. We're going to need a new seating chart pretty soon. The objects are not fusing together to one another. So there is no loss of energy. There's no Q loss in this problem because there's no deformation and no fusion. So these values should be the same. Now, how do I calculate them? Well, you think about what's going on beforehand. Both objects are moving. So I have 1/2 m1 v1i squared plus 1/2 m2 v2i squared. That's the kinetic energy beforehand. Well, let's figure out the kinetic energy afterward now. Kinetic energy after 1/2 m1 v1f squared plus 1/2 m2 v2f squared. I'll write down the number you'll get at the bottom, but you should get the same number for both. Please check that you do. If you don't, check with your neighbor on their calculator to see what you did wrong. Yeah, Jeff. You should be calculating right now.
Question, you would just say like find the energy.
I would say verify that this is true, or verify that this problem's velocities are true by finding the energies. And once you see that they're the same, you can simply say the kinetic energies are equivalent. This is true, or the statement is verified. Okay?
The suspense of getting back to the test is killing me.
It's killing you? I'm sorry.
I'm dying.
I usually don't do this, guys, and I apologize. I'm usually very good with the day after or 2 days after, but this has just been a long weekend. I was not feeling well. You guys obviously know I was not here.
Not feeling well.
No, I really was.
Long weekend of
I was away, and I got home on Sunday morning, and I had a real bad stomach bug for the next day and a half.
I hate stomach bugs.
It was not fun.
In the morning.
The afternoon the next day, relax. Now, let's go on to the next problem and take a look. Verify your answer is correct, please. Let's begin to write. Jeff, you don't need to hear it. Whatever that was just there, Jeff.
Mr.
Because I haven't heard that one before. Sorry, Jeff. I don't mean to.
It took us that long.
And that's what I mean. I used to hear that all the time. It's pronounced the same way you would howl as a wolf, I guess.
Oh, I just got it.
Oh, Paul. Let's go. Let's write. What are you guys putting this in? Is a what? Who just did that, guys? Come on.
That was not me. Yes, it was.
Let's make a deal. Next time that happens, everybody in that area can get a jug. Seriously. Please don't do that. Because I don't know who did it. You're all going to sit there and point at each other. All four of you can. Listen, I'm not doing it now. Don't do that again. It's rude. It's rude. It's impolite. It's many words like that. Okay? Do not do that, guys. Alright, so for this problem, I want to have 2 people. I need 2 volunteers for this problem. 2 volunteers. Molly, Garrett, come on up. I can choose on you for a lot of answers. Relax.
What do we do? Come to the front?
Yeah. Alright, so here's what's going to happen. Be nice, Garrett. Jeff, there's no need to exaggerate either. Be nice. Act like somebody just stabbed him. Alright, so let's go through this. So, a billiard ball, listen, a billiard ball is traveling north, so it's on a pool table, at a speed of 3 meters per second. It collides with another one that's identical. Okay? The ball that was moving immediately stops. The ball that was not moving, we want to figure out what is its velocity after it was collided with, if it was initially at rest. Okay? So we've got one object that is moving, it collides with another object, causes the other object to move, but the first object completely stops. What happened, by the way, guys? Just out of curiosity. Just so I know.
Is that what I think it is, guys? What is that?
Sit. Relax.
Oh my.
What is it? Is everything okay?
Yeah. You just Max spilled some stuff.
Is this candy?
Max spilled some stuff.
Jolly Rancher Futures?
No, that's not.
What is this, guys?
Wait, what?
What is it?
I know what that is. It's like that gel stuff. I don't know why.
What is it, Max?
It says snow.
Is it garbage? Are you keeping it? Okay, put it away.
Yeah, it's spilled. Like I actually.
All right, everybody else sit down. Let him take care of it. Let's keep going. Now, so Garrett, what I want you to do, I want somebody to give them instructions as if Garrett were the first billiard ball that's moving and Molly's the second one. Don't obviously hit her, but you know. So he's gonna obviously be moving first. Fernando, you can give the directions. What's gonna happen here? Not like how you're gonna bump into somebody, but what is physically gonna happen? How would he reenact this or enact this?
Bounce off her.
And then bounce away.
No. Oh yeah. You need to read the problem.
Garrett is the first ball.
Listen, guys.
Bounces into Molly, but he stops when Molly keeps going.
Yes. So Garrett, act as if you're walking toward Molly. He would bump into Molly, but then he stops. And then Molly keeps moving. So, before we go into the answer of this problem.
No, he goes a little bit.
Before we go into the answer of this problem, he literally bumps into the first, or the first billiard ball literally bumps into the second one moves. The first one stops immediately. So, here's what I want you to think about. Before the problem started, who had all the momentum? After the collision, who had all the momentum?
Molly.
So, would you say there's a complete transfer of momentum?
Yes.
Now, with that said, what might you hypothesize the answer to this problem might be?
Molly's the same velocity.
Yes, very good. Molly will be the same velocity as Garrett started with because all of the momentum he had transferred. All of it did. Because he was moving and she wasn't, and now she is and he's not. And they have identical masses, so they'll have identical velocity. Well done. Thank you, guys. Let's write it out to make sure. Here we go. Why do I keep writing 2? Now, again, beforehand, the first billiard ball had the momentum. So this second one was stationary. Put a big line through it, please. Afterward, the first one stopped, and the second one was now moving. So put a line through the first one afterward. This makes the equation so simple. So simple. What else do I know about this problem?
The same mass.
Same mass. So what can I do to all the masses?
Cancel.
Okay, masses are all gone. What am I left with? I'm left with this. That's it. Look at the problem. That's all you're left with. The two middle terms dropped off. The m's all canceled. Doesn't this prove what we just said? The initial velocity is the same as the final. The initial of the first object is the same as the final velocity of the second object. Pretty cool problem, right? Yes, our logic was correct. And we proved that mathematically.
So when we're playing billiards next time?
When we're playing billiards, and you hit the cue ball, and it completely stops, it means there was a full transfer of momentum into the other.
When the white ball
Continues to move?
because it always does.
Well, that's putting front spin on it, or back spin. You need to put different spins on it.
The ball never stops.
Yes, you hit the bottom of the ball, you put English on it, it'll stop it.
Backspin will stop there.
You hit the bottom of the ball, it puts a tiny bit of backspin on it, it hits the other one, it'll stop. That's going to change the momentum equation, though, surely, yeah. So we proved our logical answer mathematically. Let's take a look at our last example for today. Please write this down.
And I would always be like, can we play? And you'd be like, fine.
Please take a minute to write it down so we can move on. A pellet of mass m, and I'm telling you mass m because I want you to use m in the equation. I could have just said a pellet, and then you have to assume its mass is m. A pellet of mass m is fired with a velocity of 24 meters per second into a resting clay cart. I know, and I'm explaining this.
That means 0?
With 11 times, yeah, because it's resting. With 11 times the mass of the pellet. So the cart is obviously bigger than the pellet. So here's what we have. We've got a pellet like this. Whoops.
The pellet,
The cart.
clay is 11 and
That's what's happening initially, right? The pellet is in motion, about to hit into the cart. But then afterward, what happens to it? Read on to part B. It's going to deform, and what with the cart? What does fuse mean?
inelastic.
Stick together, which means? Inelastic. Very good, Jeff. So here's what's happening now. Initially, there was velocity, v1i of the pellet. Now, there's a final velocity of them together. Again, this velocity was 0, remember. So imagine like if you had literally like Play-Doh in the shape of a cube, and you put wheels on the bottom of it, and you took a pellet gun, and you actually shot the back of the Play-Doh, this like cube. The pellet would actually burst into it, and it would cause it to move forward. It would actually give it momentum, and that's what's happening here. You know what this is analogous to? Ballistics. What are ballistics? Anybody know?
Like it's what they use during like the army engineering.
That's how they test guns in the army with engineering. Very good with ballistics. Where else do you hear about ballistics?
Oh, I was gonna say
In the army?
Isn't it like a gun that shoots out like
Yeah.
yeah.
Ballistics, the genre of ballistics just means the study of bullets and embedding into objects. So if you have a crime scene and you see a bullet embedded a foot into the wall at an angle of 20 degrees, you can tell exactly where it was fired from, at what initial velocity, at what distance. It's pretty amazing to figure this stuff out just with ballistics. That's how forensics works. Next year, you can option to take AP Bio or forensics. Or you can take no science, I think, right? As a senior also, is that an option? But if you want to take stuff like forensics, that's the kind of stuff you might study in forensics, learning about crime scenes or learning about, why things happen and how you can trace them back to certain things. Max?
How could you find the velocity of a bullet? Alright, so let's say that there's a bullet.
There's so many ways, I can't tell you right now. But you can go into forensics. I'll leave you with that just to do it. Talk to me after class if you really want to know. I will, but we need to finish this problem first. There's a lot to do. Now, there's a way that your textbook suggests that sometimes you solve problems, and it's by setting it up like we're doing here. And you know what they do? They write this. They write before, and they write after. Before the problem started, or before the collision occurred, what object had momentum beforehand, Garrett? Pellet. The pellet only. So the pellet's mass is m, right? What's the mass of the pellet?
11.
No, m. So beforehand we have m, the mass of the pellet, times the velocity of the pellet. Do we have any momentum from the cart beforehand? No. Afterward, we have the lumped mass times Vf. How much is the mass of the pellet? Everybody, what is the mass of the pellet? What is the mass of the cart?
11.
Together that makes up? Together?
So you're adding them, Max.
Some, remember? Again, here's what we've got. Enough.
Wait, I have a question.
M1, V1I equals M1 plus M2 quantity times Vf. Okay? Jeff, go ahead.
Wait, for the first question, it says the velocity of the pellet slash cart combination.
So we have to combine the velocities.
Well, no, the velocity, this is the VF. They're stuck together afterward. We're finding the velocity of this going on right here. Sorry about that. The door doesn't close, you know. The combination of these two, Jeff. So we take the mass of the pellet, the mass of the cart. When it's fired and the actual pellet is embedded in the cart, it's going to be one object now. You could say just find the final velocity. That's one way to do it, or to think about it, Jeff. But I'm trying to make it a little easier on you by saying the combination. All right, let's continue now. What do we got here? Guys, stop. Stop. Leave it alone. Good. Guys, come on. Let's go. Focus. Paul, thank you for the answer, Paul. Tell me again. How do I get the answer, Paul? What do I do with this step?
Yes, so you just divide by 12m.
The common mistake is to try and subtract 12m. You can't. Because it's being multiplied by VF over here.
So the m's cancel to get 2. VF is 2 meters.
I know. No, it wasn't her.
Stop. Stop, guys. Come on, focus.
I know, but I saw her on the train. She was like, oh, that wasn't me, that was my friend. She did everyone on the list. I don't know. I don't know if she was the teacher though. It might have been.
Part B.
Can you repeat that?
Part B.
Wait, how do you get
In turn.
I see.
Part B says, in terms of M, find the amount of energy needed for the pellet to deform and fuse the cart. Okay, we're reading from the top. In terms of M, the amount of energy, if you were listening, you would see. Focus. In terms of M, the amount of energy needed for the pellet to deform and fuse with the cart. So we are trying to figure out, in this problem, if you go back and look at your notes, when we looked at our kinetic energies, we had this. We made this statement. For inelastic collisions, where there is some deformation or fusion, that fusion or deformation comes about from this Q loss. The Q loss is the value, okay? The Q loss is the value that we're going to be looking for here. We want to know what extra energy was needed, or what energy that was originally kinetic was lost to make the clay mold around the pellet, or make the pellet able to actually embed itself in the clay. So for this problem, we want to think about the fact that we're solving for Q loss, but the problem says in terms of M. Raising your hand, tell me, what does it mean when something says in terms of M? In terms of M.
I think you don't have to use the number you use. It's like a variable. You answer the question like for everything.
Yes, very good, Max. You're not going to use a number. In your answer, you're going to have a variable in it. You're going to have M in the answer. Let's take a look at this problem now. The kinetic energy initially. What object is moving initially? The pellet. Thank you for raising your hand. The pellet is only moving. What is the mass of the pellet? Everybody. What is the velocity of the pellet? Everybody. So that's my kinetic energy initially. Afterward, we have a combination of the two moving. Combination. Somebody raising their hand. Tell me what it's going to look like. Raising your hand for KEF. For KEF. Fernando.
12m, half 12m.
Thank you. Times.
Times 2 squared plus Q.
Loss. Very good. Well done, sir. Again, afterward, the mass of the object is now 12 times. Because the car was 11 times the mass. Remember, the car was 11m. The pellet is 1m. So together they're 12m. Let's go ahead and look and see what we get here. So we're gonna see what we get in terms of m. Check your numbers, please. Please check your numbers. Make sure you're doing this right. Square it first and then divide by 2. You cannot divide by 2 or multiply by half and then square. I'm just dropping the loss, guys. Q loss, Q. Same thing for now.
I got 2. Oh, it's looking good.
This is some rough graph, rough calculation.
Does that make you happy?
But you can do that towards the end though.
Yeah, so look at our answer, guys. What do you notice? Our answer has an M in it. So if I told you that the mass of the pellet was 0.5 or 0.05 kilograms, you would simply plug in 0.05 kilograms, and that would tell you how much energy is needed to embed it. If you were told that the mass of the pellet was 0.1 kilograms, you plug in 0.1 kilograms. You get 0.1 kilograms on 264. Now, technically, my units here are meters squared per second squared. Because I have, remember the units of 24 right here? What are the units of 24? So wouldn't those units become meters squared per second squared? So these units really have meters squared per second squared, because when you multiply them by mass of kilogram, you'll get joules as your answer. But you can leave it like that for now, that's fine. Okay, but if you actually plugged in your mass, your answer would be in joules. Write down your homework, please.
What's the acceleration? False.
Wait, Mr. Hall, the test done?
I'm sorry?
No, right?
No. I got through like a good amount of them, Ollie. But I'm going to wait to tell people their grades until later. I got through a good amount of them. Okay. Can I give you a thumbs up or down? No. My thumbs up and down may be different than your thumbs up and down.
He gives us a high five. We get over.
So walk around the room, and everybody that got over a certain amount gets a high five, and everybody else I just go.
No, if we do bad, she gives us a high five.
I think that'd be a little messed up.
I asked her one time for a high five because I said I was proud of my grade. She was like, no.
All right, so quickly, let's go over some stuff for the midterm. First, listen.
Can't wait.
Several things. First of all,
I thought it's study.
under documents and handouts, you're going to see tests 1 through 5 solutions are up.
Oh, yeah.
Hey, you said that answer.
Okay. Now, what you're going to get over the next day or two, once I post it online, is a copy of this document right here. I'm going to load it up for you right now. Hold on. Now, what it is the following. And you should really be writing this stuff down, guys. First, okay, I'm reviewing it, I'm saying it, but you should be writing things down that you need. First of all, things to study from. Okay, your old tests are the best thing to study from. After that, your notes, after that really your problem sets, then your notes, and then your labs. Anything from any of those categories can and will be on your midterm. Now, it'll be evenly distributed amongst the points. What you're going to see, what I'm going to put online for a study guide tonight is the following document. Okay, I'm going to load it right now. Hold on.